Okay, welcome back. What I want to do is to continue with electrotechnical technology, and again I'm going on with level 3. Now ignore the units 1 and so forth, because I'm not doing it in any specific order, but it should follow on hopefully once I've put all the pieces together. So treat each video as an individual video in its own merit, okay? Now here, production of a rotating magnetic field in three-phase machines. So that's what I want to be looking at today. Three-phase AC machines, okay? And again, purely here, it just says Unit 1, Application of Health and Safety and Electrical Principles, Stage 3. Now remember, health and safety is paramount. So it will become under Unit 201 or Unit 301 for health and safety. Health and safety, 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 safety every time. Okay. Now, outcome from this session, at the end of this session, the student should be able to describe the production of rotating magnetic field from a three-phase supply. Okay, so make sure you can see this in full, okay. Okay, review. Now, I'm not going to read this out to you. You can read this for yourselves, hopefully. It should be clear enough. Okay, so let me just make sure it is clear. I'll go and scan across from a close quarter point of view. Okay. Okay. Trying to make sure that you can see and read it for yourselves. Okay. Hand back, make sure we get it all in. Okay. And remember, you got zoom on your videos as well when you're viewing this, so feel free to use that at all times. Okay. Okay. Three-phase motors. The problem for motors is how to get them to self-start. We need at least two magnetic fields interacting for rotation to be produced, and a rotating magnetic field. Now, electrical power is generated as alternating waveforms AC. It is therefore easier to drive AC motors than DC machines, okay, whether that be a motor or a generator. Now, three-phase. A generator consists of three distinct electrical windings, effectively three coils. When a rotor is turned within a magnetic coil, these windings, which are 120 degrees apart, produce an EMF. EMF stands for electromotive force. Okay. Now, let's just pan back, make sure we get this into full view. Okay, first. Now, three-phase induction windings. Now, there are three AC waveforms below, but if the generator had 6 electrical windings, then we would get a 6-phase supply separated by 60 degrees. So what we're saying here is that each phase is separated by 120 degrees. The brown phase is separated from the black phase by 120 degrees. The gray phase is separated from the black phase by 120 degrees. The brown phase is separated from the gray phase by 120 degrees. Now if we gave this 6 cycles, then this would become, it would be 60, each of these would then be separated by 60 degrees. So each of these will be 60 degrees out of phase with each other. Okay, but as we only use 3 coils, then it is only 120 degrees out of phase with each coil in respective turn. Okay. Now this represents our voltage, and that's our 0 point. So you can see that the voltage is varying between 0 degrees volts, maximum and minimum values. Okay, that will be your phase angle. Okay, represented by what I call theta. I can never remember the full name of it, but for me I refer to it as theta. Look it up, make sure you have the right reference, okay, in regards to the angle. That's your little job. I can't do everything for you. Okay. So let's go into this and let's make sure we can get this in full. Okay. Yeah, I think I have. That will be maximum for me. Okay, yes. Thank you. Right. Here, the benefits are that 3-phase supplies allow for smaller machines and cables, as the loading can be spread across each of the phases. Okay. So by having 3-phase, it allows us to use smaller cables, which cuts down on cost, which cuts down on energy consumption, etc., etc., etc. Okay. Let's pan back, make sure we get a full view of this. Okay. Squirrel cage induction motor. Now there are 2 general types of 3-phase motors: wound motors and squirrel cage. That is your squirrel cage rotor, okay? Right around here, so. Okay, that's your stator, okay? And you can see that your windings is in your stator, okay? Now here, we're simply showing you the relevant angles in regards to the brown phase, gray phase, black phase. Brown phase, gray phase, black phase, and it shows a start and finish point. Now you'll see that the start point for the brown phase starts at this point, okay, but it finishes at this point. So you can almost say that in respect of the brown phase, the starting point will finish at its opposite side at that moment in time, okay. The same for this as well. The black phase will also have a starting point, but it have a finishing point which is opposite to its starting point. And this is just a cutaway view, okay? Just to give an idea as to what it would look like. Now the supply is connected to the stator of the motor. The stator is the electrical windings around the outside of the motor. These windings are fixed and don't rotate. The supply can be connected in any of one of 2 ways, star or delta. Okay. Okay. Star windings. Just pan back a bit, make sure we can get this in full. Okay. Full view. Okay, like this, it can be read. Okay. Now here it gives you U1, voltage V1, V2, V1, V2, and W1, W2. Sorry. U1, U2, V1, V2, and W1, W2. Okay. Let me just get those in first of all, okay, before I go any further. So we can make sure we get that in. Okay. Okay. Also, now this is a star connection, and here you have one coil, right, that makes up your star, and this end would be U1, and that end would be U2. So we're looking at each end of the coil that makes up that particular windings. Here we have our next winding, and that's V1, V2. That is the each end of the coil. Here we have the gray phase, which is W1 and WU2. Now you'll notice that one of the end of the coils comes to one central point for each coil, and that becomes our central point. At this point here, that becomes our earth point in regards to grounding, in regards to our three-phase star delta system here. Okay. Then each of these would then have a line running off, drop down, and run off it, as I hope you will see later on. But some of this is already in the electrical principles section as well, in regards to the playlist. So use that information. Because trying to make sure that it's in frame. Okay, thank you. Okay, good. Delta winding. Okay, and I'll just pan back so we get this in full view. Okay. In frame. Delta winding. Now here we have the same coils, but they're wired differently. One coil, let's take W2, W1, come to one end. Then we have it connected to V2, V1 to U2, and W2 to U1. Okay, so you can see that it's connected in a delta connection. Now the supply to the windings are labeled brown, black, and gray. If we connect the end of each winding to the beginning of the next, we have the windings in a delta Greek letter shape. Okay. Now again, you need to draw these diagrams out so you can see them for yourselves and you can understand the connections behind them. Of course, you will need to know how it works. And with a transformer, you have both delta and star connections within the same structure. Okay, so bear that in mind. Okay, let's just make sure we can put it in frame. Okay. Okay. And here we have three-phase sine wave. brown, black, grey, brown, black, grey, and on as it repeats itself. Okay, that's our voltage, maximum voltage, minimum voltage. Now the voltage goes positive and negative. Okay, but remember that this, because your AC goes positive and negative, you're quite right, it actually switches off in a moment in time. But because it is three-phase, it remains a continuous supply, so it never actually switches off. As one goes to zero, the other one begins to pick up from zero. Okay. But if you were dealing with your domestic lighting, for instance, then yes, your light actually will be going on and off 50 cycles per second. But because it's doing 50 cycles per second, you're not able to see that switching on and off. But if you slow it down, you can. Okay, that's what you would then call strobing. Okay, now when the supply is turned on, a three-phase supply is connected across three sets of windings. Because the windings are 120 degrees apart, the magnetic field in each winding is rising or falling at three different times. This produces a rotating magnetic field. Draw these diagrams out. It doesn't have to be scaled, as long as you understand the concept to it. And I've already shown you how to do the calculations for drawing these diagrams out in one of the principles in the playlist. And here we are showing you, what I'll be showing you here now is the resultant force which is exerted within the motor in regards to the magnetic field. So here we're looking at, that's your resultant force in respect of your brown phase, your black phase, and your grey phase. So you have a force between these coils in regards to the magnetic field which has been set up. Okay. Grey and black phase are equal in value. Grey and black. Well, I would have said that brown also would be equal in value. Okay. Of course, here we have the brown phase also at a maximum value. Now the brown phase is carrying the maximum current in the positive half cycle and is therefore producing a peak magnetizing force in line with itself, and that is here. Okay. When the brown phase is at the maximum in the positive cycle, then the grey and black phases are at half their maximum value. The arrow shows the overall or resultant magnetizing force direction. And all we're saying here is that is the force being exerted in regards to the magnetism is exerting a force on that coil that causing the motor to rotate. Without that propulsion or attraction or repulsion, then you will not get any kind of rotation. Okay. Therefore, that magnetizing force is required for rotation of a motor or a generator. Again, draw these out, do some additional research. Don't just take this as a glimpse, because on a PowerPoint you can only put so much information and you need to keep it brief. But there's a lot more to this that you can find out by your own research, and also do the calculations as well, that will allow you to understand and become more affluent in regards to motors of this type. And here we have again, all we're showing you now is the gray phase at a minimum. Now again, this is your gray phase start and gray phase finish. Okay. But remember, this is happening in so many cycles per second, very fast. Okay. And here again, all we're saying here again, the force is now exerted on the gray phase, because that's now taking the full brunt of the magnetic flux in order to generate the given voltage. Now here the gray phase is at minimum, negative half cycle, and the brown and black phases are halfway to their maximum values. The resultant force is facing towards the gray phase winding. The resultant magnetic field has moved 60 degrees clockwise. Okay. And here we are looking at now black phase at maximum. Okay, just bring that into play. Okay, we can see it. Same thing here as well. Okay, hopefully. Hand back. We get into full view. Okay, again, so just again outline the same thing previously read, but again draw your diagrams, do some additional research, do some additional work. Okay, excuse me. Again, brown phase at minimum. Okay, so all we're now showing you is the circulation of that magnetic field going around within that given motor at that point in time. Okay. Okay. And again, just the same thing repeating itself again, showing you its cycle. Okay, and I'm just moving so you can see it. Okay. And again here, black phase. Okay, the black phase is at its minimum value. The grey and brown phases are halfway towards the maximum value. The resultant field is pointing towards the black phase winding. This process will continue and the resultant field will continually move in a particular direction. If you change any two of the windings, and the direction of the magnetic field will change. If you change any two of the windings, the direction of the magnetic field will change. Okay. Here we are. Okay, all I'm going to do is just show you this. Okay, I'm hoping that I can get it close in enough. Okay, and that's your case. That's your squirrel cage rotor. Okay, and just pan back, make sure we can get it fully in. Now here we're simply showing you stator conductors, okay, and your rotation of your magnetic field, and that's your rotor rotating. Okay, so if the rotating magnetic field is going in that direction, obviously you can see that the motor is now rotating in a clockwise direction. This will create an induced EMF in the conductor, which reduces the current flow to be flowing, which causes a current to flow out of the, well, imagine an arrowhead coming towards you. Remember Fleming's right hand rule. We know the direction of the current in the conductor, and we can determine the direction of the magnetic field surrounding it. Okay, again, you did that earlier in one of the videos I've done previously. So again, read the information and look at the playlist. Okay, use that information. I'm just going a little bit, make sure we can get it full in, all in. Okay. Okay. Yes, we can. Okay, thank you. And here again, force on the conductors. Okay. All this is showing the force on the conductor is going to act to push it in the same direction as the rotating magnetic field. So, but remember, the force is already your magnetic force anyway. So that force exists because of the magnetic force that exists within the motor itself, and which is provided by the coils within the stator as well. Okay. Now I have to say that I'm a bit dubious about this, because here it's given me the direction of direction is magnetic field is that way, but it's possible that this is showing me the magnetic field around one conductor. Because here we have the magnetic field, rotation of the magnetic field is going in that direction, that is going clockwise, whereas this is indicating it's going anti-clockwise. Okay, because from my view here, I would look at this as going anti-clockwise, but again, it could be my perception of it, whereas this is definitely going clockwise. Okay, with the current coming towards you. So my view, it's possible that this may have an error here, but I could be wrong. Okay, but I will. This is now for you to determine and to be sure that we have got the right information in regards to the rotation of the motor, and you can find this out in your principles books. Okay, so sometimes there are errors given, so we have to take that on board, but for me this would be your direction, okay, which is clockwise at this moment in time. But I see what they're saying here now. If you look at this little, if you look at this here, okay, let me just go in. Okay, look at this here. Here with the current coming towards me, and you can see here that they're indicating it's the effect around one particular conductor. But when you combine the conductors together, then you get your clockwise rotation, because it's pushing against the magnetic field against this, so that there is pushing against this field, which causes the rotation to be clockwise. Okay, yes. So I don't think there's anything wrong with this. That is quite correct, and it tallies with what we can see here. Okay. Here's also right here. Okay. Make sure we can get it in. Okay. Now again, do some research for yourself. Do some additional work. Okay. That is correct. Yes. Okay. One rotor here. This is just for you to read. Again, provide you with information on it. Okay. I don't need to do anything much on this. Okay. I've done a lot already on motors, and you should see this in the electrical principles section as well. So look at the playlist. Look at the playlist. Okay. And again here, thank you. I hope you found this useful. Talk to you soon. Bye bye for now. Thank you. Bye bye.